The system consists of a tubular frame, firmly secured to the ocean floor. This frame supports a central universal transmission hub and output drive shaft. Bolted to the hub are two stainless steel wave turbines, designed to capture the maximum direct force of the wave, as well as capturing the reverse drag of the undertow. Above the wave system is the enclosed powerhouse, which contains the flywheel, the exclusive Hilton low-speed generator assembly, and the modular control circuitry. This combined wave power system is designed for longevity and is robust, durable, and able to withstand storm force impact. The turbine diameter and the blade design have been configured to respond to the driving force of every wave. Most waves will impact only the lowest section of the inbound turbine, whilst larger waves will have little or no adverse effect on the convex blades of the upper section. However, the outbound turbine is designed to respond to the undertow of the waves against the lower section, whilst the upper hemisphere of the outbound turbine will react to the high impact waves against the concave blades, combining its torque with the overall drive mechanism for greater power output. For normal operation, nearly all waves of both low and high tide will interact with only the lower section of each turbine. Except for the submerged part of the turbine, all working parts of the transmission hub are encased above the waterline and easily accessible and replaceable where necessary. Research costs will be minimised by first erecting a single powerhouse module to test the viability of the system. Once viability is confirmed, additional modules may then be added. Access to the wave power station is via a pier causeway, which is constructed progressively from the shore to the power station site and then used as a platform to erect the powerhouse modules. The transfer of power from the power station to the shore is via a permanent and secure transmission line installed along the causeway to the mainland, safe from the sea below. The finished power station comprises a multiplicity of powerhouse modules mounted side by side at the optimum wave location. The transmission hub houses two opposed cam rotors, which are secured to the turbine shafts. The diametric crown wheels are supported by the cam rotor housing, which drives the crown wheels through their bearings on their respective shafts. Balanced opposed pinions are driven by the crown gear in a unidirectional rotation, irrespective of which turbine is powering the hub. The non-engaged turbine idles in the cam housing, allowing the crown wheel assembly to rotate freely until once again the appropriate turbine is engaged by the differential flow of the waves. One pinion acts as an idling balance force, whilst the main pinion drives the output shaft. With 10-metre diameter turbines and a 1-metre diameter hub, the ratio of the crown wheels to the turbines is 10:1, thus creating a force of 10 times the input power of the wave. The pinions to crown wheels also has a 10:1 ratio, resulting in a speed output at the drive shaft of 10 times the turbine speed. This is a win-win situation right throughout the entire dynamic chain,
With an average wave power of 55 kilowatts and with 2-metre wide turbines using 10 modules, the power station will capture over 1 megawatt of wavefront, developing an estimated output of 10 gigawatt hours per annum for each power station.
Therefore, the system may provide a long-term solution to climate change with zero fuel costs and zero carbon footprint. Combined with solar and wind, many such power stations located along Australia's sparsely populated 3,000 kilometres southern coastline could easily supply the bulk of Australia's power needs on a continuous basis, without using any coal, oil, gas or nuclear power. Construction of the pier and wave power station modules will follow an identical procedure. Pier support frames will first be constructed on land and will be designed to suit the gradient of the terrain. A guide frame base will first be lowered into the water and positioned, before corner piles are then driven through the guide tubes. For this purpose, each pile tube is to be fitted with an extension to facilitate the driving process and to provide a conduit for concrete pouring before removal. If pile driving is not practical, boring bits may be lowered into the pile tubing to excavate the pile foundations. The inside of the pile tubes will then be cleaned by seawater pressure hose before concrete is poured into the footings to secure the piles in place. On completion of this work, the guide frame will be removed and the appropriate support frame lowered into place on the pile footings. After correct alignment, divers will then secure the frame to the pile footings by tightening the anchor bolts pre-located around the guide tubing. Each modular section of the causeway will then be installed section by section until the power station location is reached. Each completed section of the causeway will be used as a base for the next phase of construction work. No floating cranes should therefore be necessary. However, should it be deemed necessary at any time following installation to remove the installed modules and the pier structure, this can easily be accomplished by removing the stainless steel anchor bolts and lifting the modules out of the water one by one before being removed from the site.